explaining, I'm not sure where to talk to. That's not a big problem. 20 pages of something I don't fully understand.
I need to figure out what I'm doing for cups and stuff. I need to see how I can what I'm doing.
All right, what's everyone doing today?
In this summer.
Oh, gosh. I never watched the
I've been watching the national cheer competition.
What?
It's been entertaining.
Oh my gosh, did you watch us?
I'm surprised
Yes.
I'm
Was it
surprised
bad?
that they're all competition.
Sorry, I mean, was it good? I should have seen it.
It was not the worst one that we watched.
Ooh.
However, they did drop a girl and some effort. So it was pretty bad.
Good. Good. We were in the prelims. We weren't even competing yet. Great.
Yeah,
Okay.
Excellent.
it's great. I'm so proud. I don't know the girl's name who got hurt, but it might be Liz. Is there a Liz?
Girl, I don't know.
Yeah.
I barely know my
Yes.
kids.
She caught somebody with her head.
Ooh. Not
The computer's in my apartment, plugged up in the wall.
great. Oops.
And I was sad. What is because that means after class I can walk back to my apartment.
Okay, so today my hope is we are going to close out everything we're going to need for magnetism. And the homework for magnetism is due next Thursday. Any questions before we get started today? All right, so I recall we were discussing how electric, we've already done math for electric currents, magnetic fields acting on charged particles as the particle moves through the field. And why is it not showing on the slides? Oh, that's why. Okay. So, magnetic fields act on charges as the charges pass through the field. We can alter this into the form that is currently seen on the board right now.
Is there a reason that we use V for magnetic field?
I don't actually know what the reason is. There's usually a reason. It's just usually a reason that was a couple hundred years ago and in a different language.
Oh.
V, the symbol for magnetic field. No one's actually answering the question. The best answer that I can quickly find, there's two answers. One is a scientist named Maxwell just started using V and it stuck. The other reason is that it is short for Biot-Savart's law.
In the
Biot-Savart law is the equation describing the magnetic field generated by a constant electrical current. which is actually a formula we're going to be talking about today.
Cool, that's convenient.
That is convenient. So, when you run electrical current through a wire, that wire suddenly becomes susceptible to magnetic fields. Single charges passing through a magnetic field can have magnetic force acting on them, and the same is true for charges that just happen to be passing through a wire. Except now the wire will have the force acting on it as well. So there's just moving electrons in the wire. Current tells us how many electrons per second, times the magnetic field acting on the wire, times the length of wire inside the magnetic field. So if we were looking at this example here, where we have a magnetic field applied to a wire with current running through it, the L would be the length of wire in the field. V would be field strength, and I would be the current in the wire. And the right-hand rules still apply for where this force is going to point. Right now on the screen, we have the current pointing up, so that's the direction our fingers point. Field goes into the board, and the force should point to the left, as is shown here. If you were to reverse the current, you would reverse the direction of force. So it is exactly the same as before, just apply the wires.
Does the wire move?
Yes, with a strong enough magnetic field, the wire will visibly move. Which is why this can be a problem in electronics, because powerful magnets can make your wires and circuit components move and bend and break in ways they weren't supposed to.
When, like, you either turn off the current or like stop the magnetic field, does it go back or does it stay or does it depend on what the wire is made of?
The force would stop.
Okay.
The force would stop. That the wire might go back to normal if it's just got tension that would pull it back. It might stay that way if it has been bent. It just depends on the wire. Now, this makes circuitry complicated enough as it is.
So,
What? Sorry?
V is a vector. And the V is moving perpendicular in what plane to this wire?
So, in this picture right now, the X's represent the B field lines. And you might have missed this the other day, I apologize. X, it's hard to draw three-dimensionally on a flat board.
Yeah.
So rather than try to do 3D perspective, most physicists will use X's to show that a line is going into the screen, kind of like the tail feathers of an arrow that you fired in. And there's no picture of it. Oh, wait, I backtrack just a little. X's mean going into the board, dots mean coming out of the board, like the head of an arrow fired at you through the paper. So, looking at these pictures, the mag field points into the board, so using right-hand rules, you'll call them in. Current goes up, force goes that way. Current goes down, force goes that way. Bless you. Now this is hard enough for people designing circuits already. You definitely don't want to put any magnets next to your delicate electronics, but this is made more complicated by the fact that when you run current through a wire, it makes its own magnetic field. Bless you. Every single time you turn on a circuit, the wires of that circuit start creating their own magnetic fields. And this is ultimately the reason why wires will respond to other magnetic fields. It's because now they have their own, and the outside field interacts with its own field, and then you get a force between them. But a wire by itself, as long as you run current through it, will create its own magnetic field. And the strength of that field is given with this formula, which is actually called Biot-Savart's law. So, the magnetic field produced by a wire, this is its own field, will be equal to this constant mu sub 0. This constant is it's considered a known, very common physics constant called the permeability of free space. It comes up a lot in formulas involving magnets, electricity, gravity, the speed of light, etc. Things that move through space that don't necessarily require a physical medium. It's a known constant, 4 pi times 10 to the -7th. It will be provided to you wherever it is needed. So the magnetic field made by a wire equals that constant times the current you put through the wire divided by 2 pi and the radius from the wire. So I'll put that formula over
The
here.
radius in meters.
Yes, yes it is.
When in doubt, always meters.
When in doubt, always meters. Correct. We'll also put this constant up here. And I'm going to further label these just a little bit because this first formula This first formula describes the force from a field outside of the wire. This first formula is for when a field outside of the wire starts acting upon the wire. The second formula is for a field the wire produces all on its own. And this field does not exert a force on the wire that made it. So one wire with current running through it will make a magnetic field, and that field will not cause that one wire to start bending. Except in very weird certain situations. The reason for that is, looking at this formula, radius from the wire is on the bottom of the fraction. So the closer you are to the wire, the stronger the field gets. Except when you are the wire, the radius is 0, so the field is 0.
So if there was like a big enough wire that acted like a magnet?
Yes. The electromagnets we made in lab last week are an example of that. And it's possible with a long enough wire, if you had like one piece of wire bent such that current could go one way up the top and back down the other side, maybe one piece of the wire might affect the other piece, as long as the current was moving in different directions, possibly. But very rarely does one wire ever cause any weird feedback to itself.
In the picture, that's like a real life picture,
Yes,
what is that?
great question. This is a metal pole that is going down into the top of the table. Electric current is running through this pole, and what you see on the table are probably iron shavings or some other metal material that is now formed itself in the shape of the magnetic field that the wire is making. So this tells us that when a wire makes its own field, it doesn't necessarily come out of the North Pole and go back into a South Pole. It kind of just creates a circular spiral of magnetic field around the wire. Switch to a different slide real quick. So say that we have these wires, really I guess they're just metal posts, but if you run current through the wire, then the wire will create magnetic field that instead of going out from out from north and into south, it'll just spin around the wire in the perpendicular plane to the flow of current. So right now, the current is going up in the y-axis, so the magnetic field is spinning perpendicular to that in the zx axis. Sorry, the zx plane, excuse me. And there's a slightly modified right-hand rule to determine how the magnetic field is going to spin. Everything's still perpendicular to one another, but since the field is spinning, we have to reassign what variable goes to which part of the hand, because only your fingers are able to curl up like the field. So if you were looking at a wire and wanted to determine the way in which its field is spinning, you grab the wire, like you're just physically grabbing it, you point your thumb in the direction of current, and then the spiral your fingers make tells you the direction the field will spin in. So right now, starting from my knuckles going out, this is counterclockwise, the field spins counterclockwise. Coincidentally, most spinning things in the universe follow a similar pattern. Growing up, I always had a hard time remembering lefty-loosey, righty-tighty with screwdrivers. I have come to find out this rule works the same with screwdrivers. If you physically grab the screwdriver and stick your thumb out, if you want the screws to come out, you want to spin it this way. But if you want the screwdriver to go down, you spin it the other way. Pretty much any spiral or spinning object in the universe will follow some variation of this rule, be it a screw or a magnet.
And so it's the magnetic field that's moving in a concentric circle.
Correct. The field is moving, the wire is not. So, the reason this is of note in, say, electronics is because, well, if a circuit has more than one wire in it, the field one wire makes will affect the other wires, and vice versa. Which is why a bunch of electrical engineers have to design their circuits in such a way that all of the wires are parallel, so as to try to minimize perpendicular fields. And you want the currents to be flowing in the same direction wherever possible. And you want the wires to be just far enough apart to where the fields are too weak to do anything. So there's a lot of work that goes into designing circuit boards. As a sample, let's say we have two wires that are parallel to one another. One of them has 20 amps of current in it, the other has 10 amps of current in it. The wires themselves are parallel, just a short radius apart. And since they both have electric current in them, they will both be creating magnetic fields, and the other wire will be susceptible to the other's field because it has current running in it. So both wires are going to make fields. Both wires will be affected by the other wire's field, and so both wires are going to exert a force upon each other. We're going to figure out how much that force is. So, listing what we know and what we don't know. We have two currents. I'm going to call them current 1 and current 2. 10 amps and 20 amps. The distance between the wires is 10 centimeters. And yes, we do like meters, so what will that be? Yep, 0.1 meters. And these wires are both going to be 1 meter long, for simplicity's sake. So that is everything the question tells us. We are asked for the force between the two. On the very short list of formulas involving magnetic force on wires with currents in them, one of them has force in it, so we will start there. F equals current perpendicular to magnetic field times wire length. So first thing to determine are the fields that both wires are making perpendicular to each other, or perpendicular to the current flow.
Isn't the answer always yes?
Yes, but to just show a little bit, for this, we'll look at wire 1 to start with. Current flows that way, so its field is going to spin into the board at the top and out of the board at the bottom, if you were to keep curling your fingers around like so. So the field acting on wire 2 will be into the board, which is perpendicular to the x-axis current in wire 2. Meanwhile, wire 2, its current will also be, its mag field will also be into the board where wire 1 is, which is also perpendicular to its x-axis current. So all mag fields and all currents are perpendicular, no trigonometry required. Now, there are 2 wires present.
Wait, which way does the left go for 20?
Okay. So for the magnetic field being produced by this wire, you point your thumb in the direction of current.
Right.
My fingers are now curled like this. So on the top of the wire, the magnetic field would come out of the board. On the bottom of the wire, the field would go into the board.
Okay.
So it's
the
spinning
opposite.
helically like this. This is just to check that everything's perpendicular. It is. We don't have to do any trig. Everything, nothing cancels. We can work as normal. Bless you. Now, there are 2 wires present. The field for one will affect the current in the other. We need to, at least at the starting point, pick one of them to focus on. Ultimately, though, it's not actually going to matter which one we start it with, and I'll show why. Let's say, just as a starter, we're looking from the perspective, the force acting upon wire 1. I'll relabel these. I'm calling the lower wire. Lower wire is wire 1 because it has 10 amps, and I don't want wire 1 to have 20 amps and wire 2 to have 10 amps. So, from the perspective of wire 1, if we're looking at the force acting on wire 1, that's going to be based on the current in wire 1, but the field produced by wire 2. Because wire 1's own field won't affect itself. So from wire 1's perspective, we would need to solve for wire 2's field at its location. If we were working from wire 2's perspective, the force on wire 2 would be based on the current in wire 2 times the magnetic field produced by wire 1. So just the inverse. And it's ultimately not going to matter which one we start with, because either way, we need to solve for the magnetic field of the other wire it's producing. So we're going to have to plug in Biot-Savart's law to find it. I'm going to do that as my next step. once we plug in Biot-Savart's law, both formulas end up at the same place.
Why would you do that?
So from wire 1's perspective, we would need to find the field produced by wire 2. Wire 2's field would be based on wire 2's current and our radius from wire 2. So we would plug 20 amps in there. So the result would be 10 times mu times 20 times L over 2 pi r.
So you just plugged in B equals whatever that is into what you have right here.
Correct. I used that to replace the B in this formula. From wire 2's perspective, we would start with the 20 amps and then we would plug in Biot-Savart's law for the 10 amps. So all that would matter, all that would happen is the 10 and the 20 would swap positions, which does nothing since it's all multiplication. Which just is to say, the same force will act on both, regardless of perspective. It is a field force, and Newton's third law says, the force that one exerts on the second will be the same as the force the second exerts on the first. Equal and opposites. They're both going to exert the same force on one another. And this is just validating that. Any questions about that?
I just need you to pause long enough for me to like, I'm gonna have to write out what you did there because I
Yeah.
don't remember those.
Please go ahead, and I'll take this opportunity to get a little water.
You just start flipping.
Yes. So if you're doing it from the first one with the 10 amps, it's the 10 amps, and then the 20 amps from the other one.
Yes.
Like,
What is it?
what is that?
Okay.
And the rest of our variables.
What does TM stand for in units?
That would be Tesla times meters. So the unit of magnetic field times meters. So what amount of force are we getting? Okay?
I just don't know that I got the right answer.
Huh?
I got 4 times 10 to the negative fifth.
I got 4 times 10 to the negative 4.
That's what I have.
I have 4.
I know why. Never mind.
Fucking decimals.
Yes, okay, never mind. It's always, I actually learned another thing.
Okay. So 4 times 10 to the negative 4th newtons. Not a lot of newtons, so you as a human would never feel a force that small. But on teeny tiny circuit components over a long period of time, this might start mattering.
And then I'm gonna ask this question, and if it's gonna take you longer than 30 seconds to explain it, just tell me, don't worry about it. How do we get newtons from all those units?
Great question. I assume there's a newtons buried inside of whatever Tesla's is meant to represent. Since magnetic fields exert force on magnetic fields, there must be newtons somewhere in Tesla's.
Okay, cool.
So, I'm still not 100% clear on how you combine those two formulas. But if you just tell me if it works the same way every time, so that F is equal to current 1 times the mu constant times current 2 times length over 2 pi r. If that's just how it works every time, I can just learn that and not know why. That's fine.
It would work like that, yes. Well, what I did was, starting here, I took that formula for B, plugged it in instead,
Yeah.
and the order this is written in matches more closely to this first one, looking from wire 1's perspective.
Yeah.
Wire 1's perspective, the force on it will be determined by its current times the magnetic field of wire 2. And if we plug wire 2's variables into that formula, we would have mu times wire 2's current over 2 pi r, and then the times L.
And force 1 is equal to force 2.
Correct.
So it
They can circle
doesn't
on.
matter which one you use, just whatever information you're given.
Correct.
Okay.
And again, if we went from wire 2's perspective, we'd start with 20 times mu times 10 times L over 2 pi r. So all that would matter, all that would do is just swap the position of these two numbers, and that wouldn't change the answer at all, because it's all multiplied.
Yeah. So I have another question.
Yes.
In the mu constant, it's 4 pi, which cancels, it's like 4 pi times 10 to whatever, which cancels out 2 pi on the bottom.
Yes, so that would ultimately,
So you would
so
have 2
yeah, even
times 10
within
to the 7.
Biot-Savart's law, that would simplify to 2 times 10 to the negative 7 times I over r.
Yeah.
I don't know why they don't just write that. Physicists really like that constant, that mu constant. It shows up everywhere. It's kind of annoying because I can never remember it. I think they leave it the same because it's just a number that everyone else has memorized. So, this force will act on both wires, and the only minor detail left is, well, what direction is the force going to point in? And it's okay, I'm going to tell you. The rule for this sort of a scenario is if the current is moving, if the current in 2 different wires moves in different directions, it'll be a repulsive, repelling, wait, I looked it up earlier, I want to make sure I get it right. Okay, if the current is in the same direction, they attract. So, current in the same direction, the wires attract. Current in opposite directions, the wires repel. Because their fields would spiral in the same direction. Opposites repel, likes attract. It's the opposite to every other time in the universe. So in this specific scenario, each wire would be pushed away from the other with this much force.
But if you had wires on the opposite sides repelling in the opposite direction, would they just stay the same? Like they wouldn't?
I'm sorry, were you saying if the wires were perpendicular?
No, like, so you have these 2 wires and you just add 2 more wires on the other side that are repelling them back to the
Oh.
center.
You could create a scenario where the inner wires wouldn't move. That said, the outer wires might still move. You could create it. It's easier to just staple them in place, frankly.
which is why most circuit boards don't even use wires. They use metal pathways etched into the plastic, so that there's no risk of it moving. Any questions so far? Okay. Only a couple more things, and that's all the magnets information that you're going to need. This next part I want to pay attention to because it matters for motors and generators, and hopefully, if I can get the right wire, we're going to be building motors as our last lab for the semester. So I want to at least spend a little bit of time applying all the stuff we just did. All the stuff we just did and have been talking about is for straight lines for the most part. Current moving through straight wires, interacting with other wires, moving in straight parallel lines. Things become just a tiny bit different, just a little bit, when the wire isn't straight. So I would like you to pay closer attention to a picture that I'm about to draw. Let's say instead of running our current through a straight wire, we're going to send it into this bent rectangle. Oops. We just bent our wire into a shape, and now we're going to run current through it and expose it to a magnetic field. We know that magnetic fields acting on straight wires with current flowing through them will have a force acting upon them. And the same is going to happen here. The same will happen here. It's just a little bit more complicated now. Let's say that our wire loop is the technical term for what this is. Our wire loop is oriented in the vertical XY plane. The magnetic field will be pointing straight down along the Y-axis. And I want to look briefly at just the direction that the magnetic force will point on each part of the wire. If the current comes in along the top wire, it's going to be going to the right up here. The right-hand rules say, current to the right, field down, force goes into the board. Okay, can we go with that? I'm going to call that force equals negative Z. It's going into the board at the top of the loop. At the bottom of the loop, though, just because of the shape of this thing, the current is pointing the other way. So what direction will the force point down there? Out of the board. So different parts of the loop will have a different direction of force acting on them.
What is the little loopy thing over
That?
yeah.
Oh, that is one way that I signify vector direction. This is within the vector z-axis and pointing in the negative z-axis.
Okay. Do you want us to write that?
You could write into the board, you could use the little arrow, like the arrow X symbol to show the force would go that way. Ultimately, the point is that the force at the top of the loop goes into the board, and at the bottom of the loop comes out of the board. So what's going to happen to this thing?
Can we not just cancel out? Do we work
if both forces were acting on the object's center of mass, they would cancel out. But where this sort of thing most often comes up is when this loop is attached to some sort of apparatus that will let it rotate. As long as it has a free spinning axis down the middle, force that way at the top, force that way at the bottom, is just going to make it start spinning. So this is a motor.
So
It's
the
not
only
the-
thing it takes to like make it a motor is when it's spinning, basically?
Yes, all motors, at least electric motors, the main purpose of an electric motor is to send in electric current, and some part of the mechanism involving magnets will take that electrical energy and make something start spinning with mechanical energy. It turns electric into mechanical, or specifically rotational energy. So electric cars just have something like this inside of them that makes the wheels spin. That spinning axis is just connected to the tires.
You know, Disney World, the little like light up things where you push the button and it starts spinning. Is that just this?
Yes. All motors use all electric motors use either this or a slightly inverted version where instead of making the wire with the current spin in a magnetic field, there's a different version where you basically, kind of like what we did in lab the other week and what we're ultimately going to do. No way. That's what we're going to build next time in lab. But what we did last time in lab is we had the current running through a stationary loop and we shoved a magnet into the loop. And that made the magnet start spinning. So you're just changing which part is spinning. Yes.
Back to the electric car for a second.
Yes.
So when you're like pressing on the gas pedal, it's just sending more electric current in, making it go spin faster.
Yep.
Okay.
I guess it's not really a gas pedal anymore, but voltage pedal. Yeah, if you wanted to spin faster, you would either need to increase the magnetic field, which if you're using always on magnets, you can't really do, or you can just increase the current going through the loop. So, magnets and electricity can make things spin, which is very handy because that's how we can use electricity to make mechanical energy. Conversely, if instead of turning on current and using that electrical energy to make it spin, if you, with the system turned off, hand cranked it and forced it to spin, you would create current and turn your mechanical energy into electrical energy, thus making a motor and a generator the same machine, but backwards. So functionally, every single water wheel and windmill, those are just generators. If you, instead of them spinning by nature and taking that energy and storing it, you could use that energy to run the motor inside of it and just make them spin.
Couldn't you have like a propeller on the top of your car?
You could. That would affect your wind resistance though, so you'd be slower.
If you would not have to pay for such gas.
Correct. That said, I've seen that basic idea taken in a different direction though. See if I can find a picture instead of having to horribly draw one. There we go. way better than anything I could draw myself on a whiteboard or at all. This is a windmill. It looks like an ash tree, but it's a windmill. Each of those leaves are just kind of helical windmill blades that catch the wind and start spinning. And it's connected to the same type of machine. The wind makes the turbine spin. That makes the wire loop spin inside of a magnetic field. That produces current.
Where are those at?
I don't know where that one is specifically. What I do know is there are towns and cities that are taking this basic idea and installing these like in the middle part of roads. So like on the freeway, you've got a bunch of cars going one way, a bunch of cars going the other way, spinning up a whole lot of spiraling air in that median. You put one of these in the middle, suddenly all of that air from cars is now electricity back in your car.
Which is nice, because like the cars are gonna be driving either way.
Correct. Right now, that's just energy that's just making air move.
Is this more efficient than a regular windmill, or is it just designed?
You'd get far less energy from a normal windmill because a windmill is very high up and is using a lot higher speed wind.
But like, did they design it as a tree because that will be the most effective, or just so it would look like a tree?
So it would look like a tree. The original prototype looked something a little more like this. And just having a bunch of these on your freeway wouldn't be great with the tourism board.
Well,
What
if
if
you
you
painted
painted
them like banners, like what we have on all of our light posts.
Yeah, like you
Less,
put like
you know, the images where, like,
advertisements on
you
them.
can only read it when it's spinning. That'd be cool.
There are ways to make it more marketable. The
I
tree is
think
just
I've
one of
seen
those ways.
What? Those are all over Huntsville, like my
Really?
hometown. They're like all over the streets and like parks and parking lots.
I'm glad to hear that. These are, well, this is not the most efficient version. They could be made more efficient, but also uglier and more annoying. There's one model that they were testing in Germany where they just have this one field that is constantly being windswept. They put a bunch of a different model in that field, and rather than spinning turbines, that model is basically just a tube that shakes repeatedly, which cuts down on spinning, which cuts down on dead birds. Unfortunately, the shaking tube sounds like a vuvuzela.
What?
The annoying instrument they play, the annoying trumpet thing that they pass out at soccer games. So there was a field in Germany that was, and maybe still, just has a bunch of these weird tube turbines in them, constantly making the worst racket for miles. You cut down on dead birds, but you way increase noise pollution. Yes?
What's the difference between like the energy that this would collect as opposed to a solar panel?
Which would be more effective depends on where you are in the weather.
But like you can use energy from both of them to do the same thing.
Yeah, they're both just a way of producing electrical energy.
What if you put solar panels on the spinning blades?
That would be a very big resource cost. It would also make the blades heavier.
Okay.
I don't dislike the idea because the big giant turbines,
Those are
they're
If we
huge,
put solar panels on the top of everyone's car, they sit in the sun.
which would work great in the desert.
Right.
If you live in Seattle, not so much.
Then don't give it to the people.
Right, like
you don't deserve.
your eco needs are best.
They can have spinnies on the top of their car. People in Arizona can have solar panels.
Correct. Well, your best energy efficient model depends on where you live.
Like giblets for Crocs, you get to swap them
Yeah,
out
you
depending on
pick
where you
what
are.
energy saver you magnet to the top of your car.
That said, solar panels are expensive because of the materials that go into them.
Aren't they like
so-
really toxic to make too?
They can be.
Like, isn't it like really bad, like to produce solar panels is like really horrible for the environment?
They can be.
I read about these solar panels that are like completely clear, so you could just use it as a window,
Ooh, I like that.
which would be really cool. Also, solar roadways. It has one of the best marketing videos that I've ever watched.
I've seen someone suggest a road that was made of solar panels that could charge electric cars driving over it.
I saw that. I saw like one of my teachers in high school showed us a YouTube video about it.
Unfortunately, solar panels generate a lot of heat because they absorb the energy and then bounce some of it back. So solar panel farms are a squintillion degrees approximately. Birds have died because they flew between the sun and the panels and got fried immediately. So a solar panel road
Is that why they
would
make
melt your
them crooked like
tires
that?
and then melt you
Is
if
that
the
why
road was
they
made of
are
panels.
like this all the time? Like they're crooked? Or is that
They
just-
are crooked to follow the sun,
Oh,
or
never mind.
crooked to be in the position to get the most sun for most of the day, based on where they are located.
You know that solar panel farm like that's around here? I always pass going on like coming
I believe I've seen one before,
back.
yes.
And like Pelzer or Easley something.
Mm.
They have one. Do they use it for like the whole city or like does one company like have something like that for itself?
I don't know. Companies use them, private citizens use them. There are some private citizens who have their own panels that make enough for their house. And since they can't store the energy, because they're making too much of it, they send it back into the power grid, and the power grid pays them for it.
This one's like this big field with a ton of them in it.
I would assume that at least some of it's going into the system, either for the benefit of a person or a private company.
In Arizona, most houses have solar panels on them, but they also sometimes have solar water heaters.
Okay, does it heat things just based on the heat from the sun, or is it electricity from solar panels?
I don't know. It looks like a big black donut that's on the roof, and it
Okay, that's just
makes
warming the
hot
water from sunlight. There's no electricity involved.
I don't know. It like cycles the like it heats it up and then it like sends it like back down into the house and like so. I don't know. It's,
My solution is just use cold water.
I bet Disney World's little solar panel field, like, is like one ride. You know?
probably not even that. Because like they're always on and they take so much.
Okay.
And it's so small, but it should like make you down so nice.
Okay. This is, because there is force making something spin, that is torque. The only piece we care about is this. This is the one line we care about.
Okay.
Let me see if I can actually tweak that. Yeah, I can. Behold, the only court you need. Tiavin. That is a lowercase tau for torque. Torque? That's a dog's name?
Yeah.
Interesting.
It was weird. That dog got shot 3 times and still just like powered through.
By who?
Well, he would run away into the woods and like accidentally get shot. And then he comes after. Yeah. Usually. I mean, the dog just came back, so like, we don't know who shot him. We just was shot.
I shot the shit. And that's apparently the dog's name. They renovated this whole building, except that.
Charge times area. What is the min for in that?
That would have been so cool. Okay, hang on. We've got torque equals current times area. Really? Torque equals current times area times magnetic field times N. N, I think, is number of loops. Yes, the number of turns in your coil. And the field needs to be perpendicular to the surface area contained by your loop. So if we look at this picture here, we have our magnetic field, that's strength of B. The loop, the area of the loop would just be the area of this rectangle.
Not like the little stick part.
Come again?
It's like, not the little handle part.
Oh. We're going to electively ignore that, for simplicity's sake.
Cool.
We're going to say this rectangle is what is in the magnetic field and what is being used for power. Okay, variables, torque, which is measured in Newton meters, current running through the loop, A, area in meters squared, B, right, mag field in Teslas, N, number of loops. Newtons times meters. Torque, flashback time, torque is the angular version of force. Force makes things accelerate in straight lines, torque makes things accelerate angularly and start spinning. So spinning force equals current in loop times the area of loop times the mag field perpendicular to the loop times the number of loops. If this was just one wire going through one time, we would have an N of 1. If you wanted to increase efficiency though, you could wrap the wire around several times and multiply the output by the number of times you did that. 2 loops, twice as much torque. 3 loops, 3 times as much torque.
So it doesn't really matter like how big the loop is, just how many loops there are.
Loops would
I guess
be
it
more
comes
important.
into-
It's easier to have a higher number of loops than to have a giant area.
Is that why things are coiled?
Yes, you could, a giant coil would be the number of loops in the coil. Is that a question?
The square thing here is the loop, right?
Yes.
Is there a reason it's a square? Can it be anything?
It can be a rectangle, it can be a circle.
And the math is also the same.
Yes, however whatever shape it is, find its area, that goes here.
So if you had like a thing and it was wrapped with wires like this way and this way, and you put it in the magnet, would it spin like a gyroscope?
I'm sorry, say that again?
So like if the wires were going like that way, but we're also going the other way,
Like you doubled one back and went the other direction?
Or just like two.
like two
wires.
different axes.
I'm having trouble visualizing what you're describing.
Kind of like a basket like this.
Oh, like multiple loops inside the same, like multiple things in the same field?
Yeah. But they were like hooked together.
It might. There could be a way to design multiple loops such that they can fit into each other and keep spinning and not hit one another. There are ways to do that, but they would probably need to be, like, one loop would have to be mounted and spinning to a machine over here. One would probably have to be mounted to and spinning to something over here. And since that means you'd kind of be replacing all the magnets on this side with another loop. So you'd get more loops, but less magnetic field. So I don't know if that would be any more efficient. It could be done, I think. I just don't think it would be super efficient. Okay. Something up here is broke. Oh, yeah. We'll end on one sample question. In instead of a rectangle, we have a circle loop with a magnetic field being shot through the loop. The magnetic field is not perfectly perpendicular to the loop area. Wait, wait, where the tour? Oh, that's fine. One sec. What is? So, we have a loop. The field is being sent through the loop. We know the loop's radius. We know the current in the loop. We're going to assume it is a single loop, so n of 0, sorry, an n of 1, excuse me, an n of 1. We know current, radius, and B field strength. However, the B field is not completely perpendicular to the loop's area. I'm going to do this with you. I'm just making sure you're aware of what to do when this comes up. I'm taking that 3D drawing and making it 2D. So this is the loop as seen from the side. It's a 2D object, so it looks flat from this angle. You cool with the perspective on this?
Yes.
Okay. The B field is a vector. It equals half a Tesla. It is pointing at 30 degrees from the vertical. So we just need to figure out the vertical piece of that triangle. Cosine of adjacent is, oh, sorry, cosine of angle equals adjacent over hypotenuse. So cosine of 30 will be the y piece over 0.5. So the y component of B field will be 0.4 maybe. Trying to become more confident in my mental math. 0.43 almost.
What's the red arrow?
The vertical axis. We're dividing the B field into its components to figure out how much of it is perpendicular to the loop, because only the perpendicular portion is actually going to matter. And of this half a Tesla B field, only 0.43 Tesla are going up perpendicular through the top of the loop. So this is the B we plug into the formula. Torque equals 2 amps times our area. Area of a circle is pi r squared. Thank you. Times our new vertical B times, for simplicity, this is one loop.
Wait, the radius is 1. Oh, that's a 1. It looks like a 2. Sorry.
Sorry, that is 1 squared. My handwriting is still atrocious. I don't think it's degrading though.
Whose radius is that?
It's a system. It's not a good system, but it's a system. Fire squared, correct.
It's probably, don't worry.
How much torque are we getting?
2.7.
Good. Torque is given in Newton meters,
Oh, I put in.
Because it has to be different somehow. And so that will be the torque that will make this start spinning.
That's the maximum? No.
Correct.
Yes.
Well, at least at its current angle, that is the maximum. We will end on this piece of information though. As the loop begins spinning, we're told that this particular loop can rotate about the x-axis, so it'll spin back and forth through here. As it begins spinning, the amount of field that is perpendicular to the loop will change, which means the amount of force on the loop is going to change. Eventually, it will spin to a point where the force equals 0, and then if it keeps going, if its momentum carries it past that point, it'll enter a region where the force will tell it to turn around. The torque will be in the other direction. So, left as it is, it'll spin to the neutral point where the loop will also be at this 30-degree point, and then it'll stop.
So torque would be 0 at 30 degrees?
Correct. In order for this to be an effective motor, it needs to be able to cut the current. The current needs to turn off occasionally. Because if the current stays on in the same direction all the time, the loop is just going to get to that neutral point and stay there. But if the current shuts off while the loop still has momentum, its momentum will carry it past that point, and then you turn the current back on, and then it accelerates again. So, when we actually get to build those motors, we're going to, rather, I hope it'll be clever, we will build in a way for the current to be shut off so that momentum can carry it through that point, and it can keep spinning.
So would another way to answer that question be when the x-axis is parallel to the magnetic field?
When the loop's area is parallel to the magnetic field, yes.
Areas. Okay. This is weird.
Correct. Magnets.
Not saying it's aliens,
If it's not aliens, it's magnets. Possibly both. Both is bad.
oh, that's really cute.
Okay. That is all the important things for magnets. I might show you one cool thing next week. We will meet Thursday of next week. And on that day, we'll talk about the homework, and I will show you magnetic flux. But flux is even more vaguely defined than everything else so far, so I'm just going to show you it. I'm not going to force you to do much with it. I just think there's a cool machine that I have in the back that uses it to do something neat. So we'll wrap everything up with a demo and finishing homework. And that will be next Thursday. Questions?
Oh, we don't have classes.
We don't. Class is still Monday, so don't forget that. But do please have a nice Tuesday.
Is this the one you tried to throw away?
Yes.
Have a great weekend.
All right.
Have a great weekend.
I will. Thank you, and
When
you as
is
well.
this
next test will be the week of Honors Day. The week after next.
Thank you.
Oh,
What day of the week is Honors Day?
Wednesday. So it doesn't affect this class outside of me having 2 reasons not to have lab that week.